Thank you, Pekka. I'm grateful to the Architecture Museum and to the friends that I know here and the new friends I hope to meet, and to Matti, who I've worked with now with Pekka at great length. If I'm either eating the microphone or holding it too far, somebody just wave at me. I'm not used to using two hands. I'm not ambidextrous. I want to start with a bit of an epilogue, or prologue, I should say, which is to show this print by Brian Nash Gill. He did a beautiful series of woodblock prints of trees in a book, which I recommend that you get. But the reason I show this is because it is a little bit of the chestnut of the wood, no pun intended, the wood lecturer's chestnut. You know, you show a woodcut at the beginning of your lecture. Usually it's actually a picture of a tree, but this is actually an ink print of a literal tree. And what I like about that is that it's a bit of a dissociated, it takes away the sort of romance a little bit of the tree as this living thing. It's analytical. And I do that with intention. Because I want to talk about wood in this transcalar mode, which is to think about wood as a molecular, biochemical system, as a cellular system, and potentially as an urban system, and possibly a global system, but I'm really reaching at this point, so I'm going to be careful, and I hope you'll forgive me if I overreach. What I'm interested in is the potential synergy between two landscapes which have previously been considered in conflict, the city and the forest. And the thing to remember is that forests hold carbon and cities emit carbon. And so the question is there some way to game forest growth, sustainable harvest, to produce cities made of wood? And moreover, to try to disconnect from a building technological and industrial perspective two landscapes which are linked. The mineral extractive landscape, which produces steel and concrete, is linked to very efficient footprints, urban aggregations, urban building morphologies. And the forest, unfortunately, despite its incredible rich material range, is linked to a low-rise, low structural demand, suburban morphology. So how do we break that? And what I'd like to propose is that we break it through regenerative architecture, and in particular, a regionally regenerative architecture which cuts down on potential transport costs, which uses the feedback mechanisms of people living in forests or near forests to know if they're being over-harvested, potentially deforested. We've lost that connection. We talked a lot about that today at the World Circular Economic Forum, how people aren't paying enough attention to their natural surroundings, or I guess disturbed natural surroundings, which is most of the world. So the question really today is, how do we move from this low-rise suburban morphology, which is in America, suburbia, and it's one of America's greatest imports, or at least most durable imports around the world. We build suburban morphologies. How do we shift that material into new forms of building, which the Europeans have adopted much earlier than the Americans and the Canadians, but we're trying to catch up, and to produce high-density timber morphologies. And so I want to run this through because there's concerns about how much wood we have in the world and whether we can actually build global cities and why we would do that. And so we ran a little kind of scenario where we took a forest stand, and we planned to do a sustainable harvest, and we planned to build out a city, 4 blocks district in a city that I live in, New Haven, Connecticut. And you'll notice the comparative carbon content. And we basically ran this scenario where we made 60 plots. We cut 45, one a year, to build out the buildings based on the growth plan of the city. And we studied also the stem succession regrowth of each plot, and we calculated actually how much material was needed, and it was proved that actually the plots basically regrew, and we left quite a bit in reserve. And we started calculating how much carbon was actually moved out of the city. It started with how much was preserved in the forests that we didn't cut, how much was reabsorbed through the regrowth of the forests we did harvest, how much was sequestered in the buildings, and most importantly, how much was avoided when we didn't build with steel and concrete, which would have been the conventional building material for that neighborhood. And so we ended up with a total carbon bank of about 282,000 tons of CO2, which is equivalent to about 64,000 annual emissions of vehicles. And if you start calculating the current value of a ton of carbon, it's probably worth several $1 million. If you listen to Bill Nordhaus, a Nobel economist who described the potential for a carbon taxation scheme, he feels that by 2100, a ton of carbon will be worth something like $1,000. So I'm not going to do the math for you, but suddenly we start thinking about carbon as an economic currency, and that forest is a driver of that and incentivized to grow and be protected and restored and expanded, afforested. And so that was my long-winded way of starting my lecture, The Carbon Positive City. Another piece of art by a really interesting sculptor, James McNabb. He makes a lot of wood cabinetry, and he started collecting all the scraps from a scrap bin, and he made a city, and he photographed it. And art has something to tell us, I think, in this case. We should maybe be building cities with wood. Obviously, we should protect our forests, but maybe we should consider the possibility that we could build with wood. And so for those of you who are worried about global deforestation, I ask you to think about the fact that it actually may be a way to harvest silviculturally a lot of the forests that should be cut, obviously protecting those very biodiverse, at-risk forests in certain parts of the southern hemisphere. And in America, for example, in the US, at 1500 AD, half of the country was covered with forests. Today, we've removed a bit of it, and we're down to 33%. Right now, the US forests could sequester 11% of all the emissions associated with anthropogenic activity. But if we could potentially, with proper forest management, which includes use and harvest, we could sequester, absorb 30% of national greenhouse gas emissions. And you might ask, where's the rest of that going if the forests can't absorb it? We have other forest pools, other carbon sinks and pools, and we'll talk about that in a minute. But we should also start any discussion of using the vast usage of timber for building global cities, which will expand inevitably. We should talk about what the real forces today of deforestation are. Agricultural conversion. We eat a lot of meat, fortunately, and we need lots of pasture land. And we mine for lots of things, lots of metals. We overuse metals, actually. We know this from our circular economic friends at the Finlandia Hall. And just building itself uses a lot of forest. And of course, climate change itself has wreaked havoc on American forests. You heard about the California lake, the Camp Fire in California last year, which destroyed huge amounts of forest and released enormous amounts of carbon dioxide. But this is really deforestation, because you can cut forests and they regrow. But this is what happens when you strip the soils, which have quite a bit of carbon in it. In fact, in the temperate forests, about 50% of carbon in the forest is below ground. And so when you strip those valuable carbon-laden topsoils away, you get an irremediable landscape. And we're running out of resources. We're talking about this at Finlandia Hall during the World Circular Economic Forum. We're spawning criminal syndicates that dredge illegally and collapse habitats in Southeast Asia to provide the demand for sand for concrete in India and China. And we accumulate waste, which is a problem in itself because a lot of it biodegrades, but we also remove valuable productive biomass by covering it with this, and we also cover it with other things, like cities. And we lose the value of those soils. Not to mention that if we keep growing as a global population at the rate we are, we will need 3 times the land area if we choose to build in the same way that we're building now in the same densities. So the question is, and I say this at the risk of possibly being mechanistic, could forests be a geotechnology? Could we treat them as valuable tools that we can work to solve the climate crisis? So I'm going to interrupt myself. A few years ago, more years than I care to remember, Pekka was very kind to invite me to speak at the Alto Symposium 2012. And I titled my talk Mistaken for Craft. And it was a sort of self-critique, because I came out of the cabinet making world. I was a furniture maker and a cabinet maker, and I started a shop, and then I had middle class guilt and went to graduate school in architecture. When I got out of architecture school, for a lot of reasons, mostly a bad economy, I ended up going right back in and starting my shop again and doing cabinet work as a way of paying the bills. But I think it infected, or certainly inflected, the way I thought as a designer. I loved wood and its properties, mechanical properties, bending elasticity, hygroscopicity, all of these interesting properties of wood, and we wanted to play with it. And we also loved tools and tooling and how you could manipulate wood with adhesives or steam bending or all these kinds of ways of gaming the properties of a cellular material. But I think we also were very proud that we expanded our system boundaries of design and tried to think about sites too. We wanted to knit our buildings like a fine dovetail joint into every site we worked in. And then we wanted to make the experience of the wood part of the building that we were making. So this combination of scales felt like a kind of radical departure for us. I was a cabinet maker, but I was thinking about cabinet making at the scale of sites, building sites, and trying to knit buildings into them, while still taking enormous pleasure in very finely crafted detail. We're really proud of this house. And it is an incredible site overlooking a sort of marine coastal landscape that's a lot like Helsinki, actually. And sometimes we actually used our houses to make sites. This was a sloping meadow that overlooked the Atlantic Ocean. It was kind of hard scrabble land, and we reproduced this for a big family of New York lawyers who had bought this incredibly expensive piece of property and asked us to make a house for them. And we used different techniques to try to be sustainable in the way we thought about the weathering of wood. And we learned that yakisugi, the charred wood technique, actually doesn't really weather very well, and it falls off after a while, and you have to retorch your house. I learned that in Japan. But it's okay. And it was a big house with a lot of program, and it was complex, and we tried to be very disciplined about how we were going to make it work and fit into the landscape and create different places using, obviously, a lot of wood, and then looking out across scrub oak to the Atlantic Ocean and out into the forest around it. But, the luxury of building houses like that, which are great because you get to learn how to detail things well. You're given the time to work iteratively and productively in the way you think about detail, and you make sure, hopefully, that they perform well too. But we had a chance to build a small building for the UN Environmental Program. We were asked in last May to produce a house for, they gave us a date in the middle of July, and we said, oh great, July 2019. And they said, no, 2018. Do you have a little house, sustainable micro house around that we can show at our high-level sustainability forum at the UN Plaza? And we said, yes. But we were lying because we didn't have it. Anyway, we followed all the SDGs, the Sustainable Design Goals of the UN Environment Program and Habitat, and we basically built a small building that could be trucked onto the UN Plaza. We learned later, after we'd already committed to this, that we weren't allowed to take a truck onto the UN Plaza, so that got tricky. But it was basically prefabricated in New Haven, and it basically housed a family of four for a peri-urban situation where there might be food insecurity, safety issues, power generation insecurity, no grids. And so we imagined that somehow it was a sort of post-apocalyptic New York. So we looked at the climate zone of New York and the material supply of New York, and we went to work. So we basically designed for about 4 or 5 weeks, and we built for another 3 weeks. We sort of started, and in 3 days we moved it onto the UN Plaza. And I will never recover from that. And if you've ever, imagine taking a house, admittedly a small one, through airport security. That's kind of what it was like. My daughter, who supplied us with food, almost got arrested by the UN police. And we looked at the carbon sequestration or storage of, which wasn't much, it's a small building, it's about 21 square meters. Really kind of one story with a loft. And we distributed the local material, and we looked at different systems, solar energy systems, solar generation, obviously, radiant thermal energy, indoor air purification, natural ventilation systems, potable water collection through condensation, but also through rainwater harvesting, and then finally a farming wall. And it was surprising to get it there. It's not, I wouldn't say it's a work of craft, but what it was an idea about working quickly with little time, trying to think on your feet, try to make a decent building, a good home for somebody with a lot of options. Essentially, you can kind of see the layout, I hope, and I won't go into much detail. This is the head of the Kenyan UN Environment Program, who spent a lot of time with us. He was great, and he actually said that he wanted to move in, which was nice. And we also studied exactly how the air we measured the air quality, and it turns out that wood has really high air quality once the initial VOCs have basically diffused. And this is our little mechanical room, which had 5 car batteries and could basically keep a family of 4 powered, enclosed in their house for 5 days, and produce enough water and enough electricity for that family to live, completely self-sustaining. And we used a lot of reused materials to make the sidings, and ran out and had to get new material. It was a rush. And we had a team of people in my office, students. We worked with the Center for Ecosystems and Architecture to develop the systems, and we made the plant wall and grew plants in that for over 2 months, and basically produced a pretty decent amount of nutrients. And it was a hit, because people in New York don't expect to find a house on the UN Plaza, and they liked it a lot. And this is the Deputy Secretary of the UN tasting basil and eating tomatoes, not the green ones. And so it was a good lesson in thinking more broadly about how buildings should perform, both as how they operate and how they protect people and provide them with services, but also how they should use materials from this increasingly resource-deprived planet. And so we thought about scaling up. And in scaling up, I like to think of sort of design spirit guide, Charles and Ray Eames. My partner Lisa Gray and I have worked together since we got out of graduate school, and we wish we could collaborate like Charles and Ray Eames, the great furniture designers and filmmakers. And I love this piece of art. It's a laminated double curvature sculpture, which I would love to have on my wall and own, but can't afford now. But when we add to the aesthetic program of this beautiful piece of sculpture, and we learn that it was a leg splint designed for injured soldiers in the Second World War, it changes our view of what that aesthetic is. It makes it more, for me, meaningful. Kant called that contingent beauty. And I think the idea of contingent beauty is something that we're wrestling with a lot, because of course we want to make beautiful buildings, but we want to do no damage to the environment, and that's the goal. And of course I was focused on the technique, cutting these little relieving joints so that the wood, which doesn't bend well in 2 directions, could bend in 2 directions. And what I really like is that the lesson that the Eameses learned was something about scale, and they did this famous movie called Powers of 10, which I recommend you see, which is essentially zooming in and out of human habitation on the Earth. And then they carried it into their work, scaling from a leg splint to a chair to a fuselage for a plane or a boat hull. And they understood that the beautiful thing about architectural design and material thinking is that it scales. It can scale, and you look for the lessons in the iterations of things that scale. And so we studied the idea of stiffness in a project, which we did in the late 90s, renovation of an old firehouse for an acoustical music studio. And we bought a bunch of plywood, and we tried to see how far we could bend it in 2 directions. How stiff would it be? And we created an acoustical shell, and we modeled it physically, testing it using different techniques of sort of tuned wood mock-ups. We measured it and gave it to a Swiss acoustical engineer who promptly wrote back and said, I can't model this, it's too complex. And so we essentially used these different threaded rod systems to produce an acoustical shell that was acoustically dead for a recording studio and very live for performance, and that was a kind of complex design process. And we designed an acoustical diffuser at the stage to produce these sort of vanes which twisted and warped to diffuse sound for the musicians, and also to serve as an air return duct. And we stole a little detail from one of Charles and Ray Eames' furniture patterns, which was this relieving cut where we cut a circle out of the end of a kerf cut, saw cut, because we found that when we were warping that, it split. But when we could expand the tensile area around a larger surface area, it wouldn't split. And that became a kind of motif. And the room seats about 70 people, and a crush, and the piano you can hear. It's incredibly how live, how rich wood is, and we know it's a great instrument material. And here was a big room that was an instrument. You can hear the hammers on the piano coming down before it hits the string. And it's so incredible. And we were renovating this firehouse, which had been abandoned, and we were able to, through the brilliance of our client, Nick Lloyd, who runs a record label there, produce essentially a home for himself and his wife, who's a painter, and then their children, and a bar in the basement, and the recording studio, and the record label, and visiting musicians started coming, and it was really successful because of his vision. And he lived in this amazing sort of relic of 19th century New Haven industrial space. And he asked us, once he decided that he was going to house visiting musicians instead of making them pay exorbitant hotel prices in New Haven while they were visiting, he asked us to build a dormitory with 3 bedrooms on top of the building. And we quickly found out that the building couldn't support, because it was an unreinforced masonry building. And so we chose to use mass timber, cross-laminated timber and glulam, to stiffen the building with a light structural material that would essentially keep the building up under the load that it held. So we have a stairway up into a hallway and with a little seating area for musicians to play, a couple of 3 bedrooms and a little bathroom and a WC. And it's sort of created this new urban lawn on the roofs, and it's created more density. And what was the real discovery was we could plop this building down on top of an unreinforced brick building from, 100 years, built 100 years earlier. And so a developer contacted us and said, I want to add 2 stories to the other building next door. And we designed a sort of restraining system using cross-laminated timber cores to produce a hotel 2 buildings down. And then another developer called us and we designed another building, and I won't go into the details, but suddenly the city economic development coordinator was saying, oh my God, we can actually get more density in our city using wood because we can't do it with steel, it's too heavy, or concrete. So this is a great model, and we'd like to pursue it. And that brought us to a kind of idea about this notion of structural biomass. Like, why aren't we using this great plant material that's so abundant and so photosynthetically productive? It provides so many ecosystem services. Why aren't we using it for our buildings? Because we know that it will regrow, it will regenerate. We've been talking about renewable materials for 60 years. And so we began to study different scales of using just round wood to produce structure. That was a school. We worked to produce this apostolic community center for some Jesuit priests who said they wanted to be stewards of the environment and they wanted to be, follow their vows of poverty and celibacy. And that reminds me of a kind of funny story. We were having dinner with the rector, and we had a really nice bottle of wine while we were talking about the design. And another visitor who was a lay person, after this sumptuous meal, said, man, if you guys do celibacy like you do poverty, sign me up. Anyway, the building is a lot of wood. We designed it as a wood structure. The university that sponsored the building decided that it wanted to do a LEED platinum building, and we learned that you get more credits for recycled steel, despite the enormous smelting energies that go into steel recycling, than you do for a wood structure, because wood was essentially politically knocked out of LEED for quite a while. Recently it's been reintegrated through a material credit. And And so we made a steel building and we used as much wood as we could. But what we found was that the university had essentially, through bad planning and soil management, had killed a few enormous American beech trees, which they were going to cut down and chip. And we decided to turn it into components of the chapel because, the Jesuits were talking about poverty. So we wanted to deal with this issue of scarcity through the wood, and we studied all the different kinds of flaws that exist in lumber and embraced them. Creating screens, privacy screens for the chapel and for the men between the public spaces and the more sacred spaces, and the altar and the ambo and the crucifix and the baptistry, baptismal font. And the idea was to embrace all of the material coming out of the forest, not just the superfine, the sort of rock star trees that everyone wants in their beautiful cabinets in Manhattan, in their kitchens and bathrooms, but to try to understand how we might use solid wood with flaw, with spalting and rot, and consolidate it into a meaningful piece of furniture. But the thing that really gets us excited is the technology of contemporary wood engineering and glue. And when we saw this, I showed this in 2012 at the Alto Symposium, when we saw this famous experiment, which Juhani Palasma called the man-made tree. We saw it as a sort of repository of lots of adhesives, lots of technically interesting adhesive. And we went to work thinking about all of the different things that are going on around the world, inventions, the sort of revolution in bio-based materials, biogenic materials, which is happening right here in Helsinki at VTT, or across the Atlantic at the University of Maine in Arno, which found a way to mechanically produce nanocellulose and are pressing panels out of it, or the work by the folks at the TU in Munich on cellular nanostructural modification of cell walls using polymers and mineralization to create greater rot resistance and fire resistance and all these kinds of exciting things, and these different techniques of adhering wood. We're even starting to look at lignin-based glue so that we're not actually using fossil hydrocarbons to make glue. And then Achim Menges' work at the Institute for Computational Design, where he's looking at the sort of natural hygroscopicity of the water-loving character of wood and how it can change to produce apertures depending on activated by moisture changes. But I like the dumb stuff. I like the stuff that's ready at hand that we're making. We've been making glulam beams for a century. We've been making CLT for 25 years. Petra, you can correct me on that, but it's been decades, let's say, we've been doing this stuff. And really the tool is a finger joiner to make long sticks and glue to laminate the sticks together to produce massive members with enormous capacity. And now we're only realizing that we can use them in the way we used heavy timber industrially in the 19th century. It's fire resistive. And it already knows how to manipulate the different quality of fiber that comes out of the forest by putting the best stuff along the structurally most demanding edges, tension edge, the second best stuff along the compression edge in a beam, and then you can kind of load the cheaper stuff in the middle, which means you're using more of the forest that you cut. And I think we haven't yet fully understood all of the potential of that capacity that we've been using for years, creating different kinds of structural configurations. And this is an example at Bloomer Lehmann in Switzerland, a 5-story building that the architects and the manufacturing company recognized that they were using a lot of spruce, which is a wonderful structural wood, but there's a lot of beech growing in European forests, and so how could they use beech? And they made laminated veneer lumber, bearing plates, and laminated veneer beech dowels to produce a 5-story building that had no steel. And so we started making lots of buildings out of curvy glulams because we liked the shapes, and we made houses out of it, and I think our clients tolerated it. And we misunderstood certain kinds of things aesthetically because we liked the shape of this beam lying on the ground before it was put up. And so we made a bridge out of it and sort of gained the capacity of the manufacturer to produce a construction bridge that is a 10-ton, US ton capacity bridge, which we watched a 30-ton truck drive over, which was very interesting. But what happened was it kind of sprung back into shape, and we thought, oh, wood actually is resilient structurally. And so we made a number of bridges. And I'll move through this quickly. It's a kind of passion of ours. We get asked to make bridges because people think wood bridges should be in woods. It's the, I don't know, correlation that people seem to like. And we really worked with our partners as glue laminators to produce essentially treated bridge systems. And we made our first suspension bridge a few years ago, and it was a challenge. Our company, Jig Design Build, rigged it. We have one of the builders here in the audience. But we got it straightened out, and we made this bridge named after Henry David Thoreau, one of the pioneer environmentalists in the US. And people use it, and they love it, and I think they love it because it's not made of plastic like a number of the other bridges up and down the river. And it's made of solid, thick material, which, because there are not a lot of little joints, it's more resilient. It lasts longer. It's more durable. So mass timber has a lot of possibilities. And then, you know, the CLT revolution comes along, and the Americans figured it out, I don't know, like 18 months ago, it feels like. Meanwhile, Stora Enso and KLH and a lot of European manufacturers have perfected it and can still beat the pricing of American CLT manufacturers. And they just stole the idea of plywood, transverse lamination, and they produced it with sticks, as you all know. And you can produce all kinds of fascinating configurations. These slides are so outdated now, given what's available. I need to get on the stick and find some new pictures. But we're starting to build bigger buildings. This is the Arbora building by Nordique Structures in Montreal, 7 stories over a podium, 500,000 square feet, produced incredibly quickly. And meanwhile, we were building in the city these little tiny buildings, kind of bespoke community buildings, a merry-go-round building made out of just posts that canted to create structural lateral resistance. We gave them the engineers a nice thick roof structure so that they could use timber, and they made it out of steel anyway, because that's one of the issues. And we had a great fabricator in Quebec who worked with some Belgian and Austrian fabricator and French fabricators to produce this cupola made out of a kind of topography of cross-laminated timber, which had 3 skylights and which sort of spun and rotated in the opposite direction of the merry-go-round. And it's the kind of thing that shows you that wood, because of the manufacturing capacities it allows, it's so amenable to digital kinds of fabrication that it's easy to build something like that in a factory, off-site, ship it, and with a precision to be able to produce this in a matter of days. A fabrication project done in a factory, but assembled by steel riggers, because the company that was the company Can-Am, which is the largest steel manufacturer in North America, has bought a timber fabrication company as a kind of climate change scenario, because they know that wood is going to be the thing of the future, and they know that their guys know how to lift really big pieces of material high in the air with cranes. And so we made this and built this building, and took a long time to convince anyone in the city of Stamford, Connecticut, which is a city of about 200,000 greater metro area, to build this for the kids. It's a public merry-go-round. It costs 25 cents to ride on, and they ride around, and I look up and I get a little seasick, but the kids seem to like it. So here we are. We've been experimenting with making wood in the city in kind of little stabs. Meanwhile, our friends in Vancouver and Austria are building multi-story, huge buildings out of timber, and we're playing around with 1-story event spaces. But what was interesting to us as we watched the proliferation of wood architecture was the sort of molecular aspect of wood. It's made of carbon. Half of it is carbon. It's a carbohydrate, like spaghetti. And carbon is an interesting element. It's the 15th most prevalent in the world, and it's the 4th most prevalent in the universe. And it's called king carbon because it produces an array of different kinds of polymers at Earth's temperatures and pressures. And so it's abundant, hyperabundant. And when it's hard and transparent like diamond, in its allotrope of diamond, or soft and dense like graphite, you know that it exists everywhere in many kinds of conditions. A colleague of mine, an industrial ecologist at Yale, Tom Gradle, who's sort of one of the early thinkers about life cycle assessment and material flow analysis for industry, likes to hold up his cell phone and say that nearly all of the elements in the periodic table are in this cell phone, short of the radioactive ones, which is a kind of daunting thing to think about, given that most of the buildings we make today are much more sophisticated than our cell phones. They have much more material, a much wider range of material. And if you think about the throwaway culture of cell phones and you start applying it to building, it gets a little scary. So we could talk about all the buildings, all the materials that go into building, but I'd like to talk about carbon because that's the subject of my talk. And I want to just note, this is a great slide from Matti Kuitunen describing the different carbon pools that exist in the Earth, and that we've been playing a game where we have manipulated, if there was ever a homeostatic balance within those carbon pools, we've manipulated them. So that now we have a very limited time before we fully overload our atmosphere, already heavily burdened with carbon dioxide. And that's an important thing to remember. And we've seen since the Industrial Revolution a sudden spike in carbon concentration. And not surprisingly, if you also map global population against carbon concentration, you'll see that it's coupled. And that's the thing that people in the industrial ecology world and environmental world are worried about, because that means that when we consume as a species, we produce, not just because we breathe, because we make a lot of stuff, we're makers, homo faber, we emit carbon. And that correlation is very strong. And if you think about it globally, we know that over history, if you think of this as a timeline of the forest landscape, the biomass landscape that suddenly turns into the tall building, the Burj Khalifa is there. I learned from one of the engineers on the Burj Khalifa that when they pumped the concrete in the desert heat up to the upper floors through a pump line, they had to actually jacket the pump with ice water because the concrete would overheat and cure. And I think when you are making a building in which you have to put ice, you have to ice your concrete, I think we're in a very serious societal problem, economic, political problem. And in doing so, we've actually dug down through that precious layer of bio-rich soil to create a kind of hole for ourselves. And then these are all the different material classes. We start with wood and we move all the way down to the fossil hydrocarbons that fuel manufacture. And we learn basically that we have dug ourselves into a deep whole, existential, environmental, global. In fact, it's been noted by many scientists that human beings have now disturbed every geobiological, geochemical, and geophysical system short of the tides. Anyway, back to my point, sorry about that. So this is a strength-to-weight ratio of concrete and steel and wood. And we know that wood has a really high specific density, strength-to-weight ratio. But if you take into account span versus carbon emissions or carbon footprint, you learn that a wood beam actually spans a lot longer than a piece of concrete. And it's a sort of conceptual model, but basically what we're saying is you get more environmentalism, less carbon footprint for the spans that you get out of mass timber, which should be an economic incentive for anybody. And if you just remember that basically half a metric ton of carbon is stored, carbon dioxide is stored in a metric ton of mass timber, or choose your unit, we can start thinking about how wood, as well as carbon, can be a bit of a currency. And so I want to tell a story, which Matti will be commenting on soon, about a school that we made. It was a farm school in New Haven, Connecticut, serving inner city kids who have very little access to farms or nature, and they study ecology and agriculture. And they asked us to build a building for them on this site, a former farm site. Their classrooms were here in this old building. There were their farm fields. Basically, it was a dump that had been excavated out of a mountainside, and so there were lots of drainage problems. And they asked us to build an ecological building. And so we designed a classroom building which had a gym. They could only afford a half gym, art classrooms, 2 science classrooms, offices, and that it would create a new space of entry for the school because they were parked on a hillside. And so we used the building to navigate that sectional change. And it's fairly simple. I won't go into too much detail, but just to give you a little reference, you know, the building has this half basketball court, which also serves as a gymnasium and a rec space and a theater. And then most of the offices and bathrooms are downstairs, and then upstairs are classrooms, which each look into different areas. And we decided that we're going to throw everything at this building. The roof was going to become a really important element in the building. It was going to allow, obviously, natural daylight to reduce electrical illumination costs. It was going to be super, super insulated so we could, and airtight so that we could optimize our thermal performance. We lined it on the south. The roof pitches optimize the angle for solar photovoltaic arrays, which would power the geothermal pumps that ran the school. I mean, it's really hard. American school systems are a wreck. So the idea that a public charter school could get the bond issued to produce the school was a big deal, and it was really a tribute to the administrative team. They were incredible, and we've got all this stuff in there, and we developed bioremediation pools and artificial wetlands, which became outdoor classrooms. But we argued that the thing that would be the most beneficial was to use regionally harvested wood to build the building and to use it as densely as possible and to use these new technologies that would allow the structure to be the finish as well as the structure, that we wouldn't have to cover it up. And so we looked at black spruce from Canada, not too far away from us, about 580 miles, and a manufacturing company that was using this black spruce that grows in little thin strips, 8 inches in diameter maximum, very tiny. No one in their right mind would harvest a piece of wood like that. But that's where they work, and they figured out really wonderful lamination systems. And we studied how long it would take to optimize growth, how to optimize carbon sequestration in the forest, when we should harvest it, how much carbon would be stored for all the species that went into the building. And then we began a kind of transfer of that material conceptually through all of the different products that we were using, from finishes to structural components, into the building, and we tracked exactly how much carbon would go in and through the forest. So this is what we are calling the carbon transect. We measure off that line. This is the stored carbon. This is the emitted carbon during production and transport, and this is the carbon that gets stored through the body of the building. So we learned we get to store quite a bit of carbon. And we took into account the fact that the material was manufactured in Quebec, produced in Walpole, New Hampshire, and then shipped to New Haven. And this is the story of the construction. 5 guys and a crane. The whole assembly was put together in 2 weeks. And then the sidings went on, and we learned that, there's a whole way of getting more advantage, getting more to optimize more the prefabrication, which we would do next time. And the building now functions for 220 high school students and 15,000 New Haven residents every year through different kinds of programs, camp and farming programs. And the building is made out of wood. This is a glue laminated bridge which replaces what would have been a concrete egress stair. And we have a little bit of steel in there because wood can't do, when architects like to make things very thin, wood might not be able to do that. And the building is lined with cross-laminated timber. It's really an industrial product. As if there were an exposed brick wall, we would love it, right? But wood structure, people don't think about so much. These are just big plates of wood that reflect light beautifully, treated very cheaply for this rather resource-deprived school. And all the sort of public circulation spaces are made out of wood, cellulose fiber, and there's some concrete in here too. We'll be talking about that. It's really interesting. When we finished the school and we wandered around and the kids were talking about all the ecological principles that went into it, we would ask them, what do you like most about the school? Hoping that they would say, oh, the daylight is beautiful. Oh, we love the shapes. The roof shape is so cool. To the one, they said that they thought the buildings smelled good. And that was an insight that we started thinking about a little more, about this idea that we know about through the work of great people at Alta University, that the absorption and desorption of ambient humidity, because wood likes to give off and absorb water, actually stabilizes indoor air humidity, which might lead to less sick building syndrome and a natural way of buffering swings in ambient humidity. And we've also learned that with this property comes a phase change from vapor to liquid in the cells of wood, and that may have energy implications, so-called hygrothermal mass, which is just being studied here in Alta University and other places at the Norwegian University of Science and Technology. Christina Nora is a colleague. But basically it's just a building, right? It's a building that could be built out of wood easily. It's not a big deal. It happened to be one of the first buildings in the US to use cross-laminated timber. But it's otherwise just a nice place. We're proud of it. The kids seem to like it. The teachers like it. They celebrate graduation inside that room unless it's really sunny, and then that's where the speaker stands. But there's a kid playing basketball, and it's a farm school. But what we decided to do was, with the help of Matti Kuiten, is essentially conceptually take the building apart to try to understand what its impacts really are. And so through this carbon book project that Matti and Pekka and a colleague of mine in the US are working on, we started studying actually the impacts of the building. And we looked at what elements in specific were emitting carbon, and Matti will talk more about this and with much more insight than I can offer. And it's, as you'd expect, electrical elements require a lot of heat for formation. Site and groundworks can just disturb a lot of soil, and we pave things, so we lose carbon that way. And concrete foundations are a big producer of emissions. But if you look at storage, now it shows a different picture. These offsets start to become really valuable because the wood material and also the plantings and the new very productive soils that we tried to protect with the farmland and with the wetlands actually can store carbon. And so we made this sort of monstrous drawing, which is everything below the line stores carbon, everything above the line emits carbon, and if it's bigger, it stores more carbon. It's one of those useless drawings that architects like to make. I like it a lot. But it's really a way of saying that there's a monstrous condition happening, which is that we can store and emit carbon at our will. And that at our will is a really important part of this discussion. And this young guy worked on a study with us. He took our building information model, we taught him how to do it, and he quantified all of the material, and he counted up all the weight of the wood in the building, and he learned that there was 450 metric tons of carbon dioxide stored in the building, which is worth 100 cars' annual emissions, which is a great project-based educational opportunity for kids. I think he's going to be a major scientist. This guy was amazing. And that brings me to really the end of what I want to talk about, which is this idea of bioeconomic building scaled up to some of the themes, and this relationship we talked about. And I quote Lionel Robbins, who is the founder of the London School of Economics and who defined economics as a science which studies human behavior as a relationship between ends and scarce means and alternative uses. And that's what we're talking about today as a planet. And so we took our common ground model and we started studying exactly how much carbon we could store, how often we could replenish a harvested forest cut, how to move those forests of different species through our commercial products that are available right now into buildings. And we looked at suburbs, more suburban kinds of structural morphologies and assemblies. And then we looked at high mid-rise buildings. And you can see, remember my carbon transect, that below this line are the storages. So this upper line is a reflection of cyclical growth and death of forest fiber, which emits carbon. So whenever it jogs back up, it's emitting the carbon because it's rotting aerobically, mostly. And this is what happens if you don't let the logs lie in the forest and rot, but you actually use them productively. Again, I'm showing my technological bias, so forgive me. This is what's stored as we shift this material into these large urban buildings. And so we thought, okay, what would happen? And this is just a thought exercise, so forgive me, but we actually did a paper called Building a Global Carbon Sink with a group of European scientists and some American scientists. And we basically tried to imagine how much wood we would need to build all the buildings required to house the new global population explosion, the next 2 billion people who are going to inhabit the Earth. And this, again, is a carbon transect. Below it is carbon absorbed and stored. Above it is carbon emitted. This is already out of date. This was drawn in 2017. We've surpassed 400 parts per million in the atmosphere, which is 50 parts per million above what is considered a sustainable density. And that's the 2-degree that we came up with, the 2-degree temperature rise, which has now been revised by the SR15 IPCC report to 1.5 degrees so that we can save some of the Pacific Island nations from being over inundated with seawater. And then we looked at how much carbon could be sequestered if we built all the new, just buildings, occupied buildings, not infrastructure. And it was an estimate, of course, and we learned we could, basically within a range, store about 5 gigatons of carbon in the built environment, which, by the way, we're going to build anyway, right? So it's either going to get emitted or it's going to get stored. And then we looked at what would happen if we use this biomass scenario. What would happen to the upward accelerating curvature of emissions? And we found that we bent it down. Now, this again is an average, so you have to forgive the license I'm taking in talking about this. The point is, we're going to build a lot of buildings, we're going to emit a lot of carbon, and we can store a lot of carbon, and if we can forest the world's forests, the right forests, sustainably. So that temperate zone, and the boreal forest here is going to be an important provider, and we'll use the mechanisms of global economics and exchange to hopefully transition to post-agricultural waste products in the global south where there's less timber. We have a colleague in Indonesia right now who's making rattan glulam, which is a weed. And so in a sense what we've done is we've rewritten the history, or we're rewriting a future history of global carbon. Starting with the Carboniferous era, where the fern-like trees and the sort of low number of aerobic bacteria that wouldn't digest cellulose basically consolidated into this vast fossil hydrocarbon pool in our lithography, in our lithosphere, and to the point of the Industrial Revolution where we start digging out that fossil hydrocarbon and emitting it to build our buildings and fuel the manufacturing processes. And then finally, through a new set of kinds of assemblies that maybe we can use, again, carefully, to produce a new biospheric building, which relies largely on renewable resources as well as industrial waste streams. So, to this economic exchange, we know in the eastern seaboard of the United States, I think it's less of an issue in Finland, but in the US, we have flooding all the time. And architects love to adapt to climate change. They talk about resiliency as a means of getting more work. We can build our way out of this problem, and yet we'll just exacerbate the problem in the process. I love to do the life cycle assessment on this concrete seawall. It will certainly last for a while, we hope. And then the other option, which I think is less considered by architects and environmentalists, is that the built environment could mitigate climate change, which is what I'm talking about. And what does mitigation look like? It probably looks like a robust forestry, sustainable forestry system, incentivized forest restoration and afforestation, growth of new forests. And it has a lot of great, hopefully pleasing wood architecture in beautiful convivial densities like Helsinki. Thank you.